Welcome to the 5.2 day one notes. We're going to be looking at some more trig identities. These are called the sum and difference identities, sum and difference of two different angles. So there's some there's a nice little video here that you could watch that kind of helps explain where some of these come from that I'm not going to explain. Not going to take the time on this video to show that video, but it is recommended that you go and that you watch that. There is some good information on there. So here are the formulas that we're going to be using today. So for cosine, if you have two different angles and you're subtracting those angles before you take the cosine, keep in mind this is the argument right in here. So alpha and beta are two different angles. If we subtract them first and then we take the cosine of the resulting angle, we could actually find that without actually knowing what that difference angle's cosine is by taking the cosine of the first times the cosine of the second plus the sine of the first times the sine of the second. So something about this cosine formula is, notice that with cosine, we take cosine of both of them first, then we take the sine of both of them, and this subtraction changes to addition, which is definitely important. In a similar sense, if we're starting with addition, same formula, cosine of each angle, the product of that first, followed by the sine of each of those angles, that product. But this time, we're subtracting. So whatever the starting sign here is, we are actually going to change that sign in the middle. That's always true for cosine. So those are actually, if you memorize one of them, you can kind of memorize both of them for cosine. For sine, it is a slightly different pattern, but there is a pattern. So if we take two angles and we find their sum, and that becomes our new argument, and we take the sine of that resulting sum, we could also find that by doing the sine of the first times the cosine of the second. We're going to keep this as addition as it started off, which is different than the cosine sum and difference formulas. And then we're still going to be working with each angle, but we're going to do the cosine of the first one times the sine of the second. The subtraction one, the difference formula, same pattern, but again, we keep the same original. Since this one starts off subtraction, this one stays subtraction. With cosine, that's a switch. With sine, you keep the sign the same. The tangent one, the tangent formulas, again, if you memorize the sum pattern, the difference pattern is just the same thing, we just have to change the signs. So for the sine one, we're going to start off with an addition on the numerator of the tangent of each of these angles individually. The denominator, you're going to want to memorize this, will always start with a 1, and then if we are starting off, if this is a sum formula, this becomes a difference. And then it's the product of the tangents of both of those angles. The difference formula, the pattern stays the same. So since we're starting off with subtraction, on that numerator, it is subtraction. On the denominator, it becomes addition. And so that will always be true, where the one on the denominator for the tangent formulas is the different sign. So here's why this is useful. We might have something where we are trying to find the cosine of an angle, but it's an angle that is not part of the angles that we've memorized as part of our unit circle. So for example, we're trying to find the cosine of 15 degrees. So this could be written like this. It could also be written cosine of 15 degrees. So just so you see the different ways that it could be written. Well, this is not one that I have memorized, and this is without a calculator. And in fact, your test, you will be not able to use a calculator on your chapter 5 test. So we have to have a way to do this without using a calculator. So we're going to use one of the formulas. We could use a sum or a difference formula here. We want to use angles that we do know the cosine and the sine for in our unit circle. So one way we could do this is we could think of the cosine of 15 degrees as being the cosine of 60 degrees minus 45 degrees, because those are both ones that we know. So quick reminder, 45 degrees is your easiest one. The cosine is root 2 over 2, as is the sine. 60-degree angle depending on kind of what pattern you use for memorizing this. I use 3, 2, 1 for cosine and 1, 2, 3 for sine. And so there's my sine and my cosine. So what I want to do here is I'm going to just write out the formula. I'm needing to do the cosine of 60 times the sine of 40, or sorry, times the cosine of 45. So the pattern for cosine is it's cosine of both of them first, and then we change from subtraction to addition, and we do the sine of each of those. Well, the cosine of 60 is 1/2. Cosine of 45 is root 2 over 2. Sine of 60 is root 3 over 2, and sine of 45 is root 2 over 2. So as I simplify this a little bit, I end up with root 2 over 4. And in fact, these both have a denominator 4 plus root 6. Every once in a while, you might see this written oddly where there's like a GCF. That's kind of a weird one. If you ever see this answer, it's equivalent. You can write the answer in any form you'd like. I probably would write the first one. So this one, a little bit differently, is asking us to work backwards. These are degree angles here. And so what we want to do is we want to figure out, what is this? Well, this matches the cosine formula since it's cosine, cosine, and then sine, sine. So this is a cosine formula using the angles of 155. And since this is addition here, we are really doing the difference formula. So really this is the cosine of 45 degrees, which is root 2 over 2. So this is just asking us to identify what formula we're using and then do that subtraction and then take the cosine from there. All right, here's one where we want to verify the identity. Now you could work on the left side or you could work on the right side, but we do want to go through this and try to use some of our formulas. I'm going to recommend you use the left side. You can go ahead and pause the video and give this a try. When you're ready, restart the video. All right, so I just did the first step here. I substituted in the trig identity that matches this. I'm just kind of watch that sign change in here. And then because this is a ratio, both of these portions are being divided by cosine alpha, cosine beta. So now I maybe wouldn't show this step every single time, but it might be a good idea to have it down on your notes so that when you later on are going back and looking at this, you can kind of see, what did I do? But really, each of these individual parts of the sum are divided by that same denominator. So the first one ends up equaling 1 because we're dividing by itself. The other, if I check the arguments to make sure they're the same, I have sine over cosine with alpha and sine over cosine with beta, which those are both tangent. Keep that argument in there each time, as every trig function requires an argument. Oops, that would be a tangent. And that is a match. And so this is good. All right, this one, kind of similar to number 3. We want to try to find, maybe we're going to use either the sum or the difference formulas to try to figure out what would this be able to become 5 pi over 12. Could we add two angles that we already know in our unit circle in radians, or could we subtract them in order to rewrite this as a sign of either a sum or a difference? I'm going to pause the video, give that a try. So I'll talk you through my thought process as I try to figure out maybe what angles would be adding and subtracting. So in our unit circle, for our memorized values, we don't have any with a denominator of 12. So I decided to use a denominator of 4 and a denominator of 3. And I believe you probably could have figured this out with the denominator of 2 and 6 as well. So there should be more than one. There are times that there's more than one correct way to get to this answer. So pi over 4 angles and pi over 3 angles could give me a denominator of 12. If I multiplied the top and the bottom by the other angle's denominator. So there's my pi over 12. Now, right now, if I add this, it'd be 7 pi over 4. If I subtract it, it'd be negative pi over, or 7 pi over 12, or negative pi over 12. But what if I multiplied this numerator by a different one? Because we know lots of different multipliers of the pi over 4 angle. So what if I made this 3 pi over 4 to start off with? Then when I enlarge this to get a common denominator, I'd get 9 pi over 12 minus 4 pi over 12, which would be the sine of 9 minus 4 would be 5 pi over 12. And that's what I'm looking for. So that's what I decided to do, is to really start off with the sine of 3 pi over 4 minus pi over 3. And when I get that common denominator and subtract, it ends up giving me the sine of 5 pi over 12 that I'm looking for. So I'm going to use the sine formula. So it's a slightly different pattern than the cosine formula. So I'll do the sine of the first angle times the cosine of the second angle. This starts off a difference and it remains a difference. And then I do the cosine of the first angle times the sine of the second angle. And so I'll just do a little pre-planning. 3 pi over 4 is over here, which has the coordinates, since it's a pi over 4, negative root 2 over 2, root 2 over 2. And then pi over 3 is that 60-degree angle that we used a minute ago in a previous problem, which is 1/2 and root 3 over 2 for the cosine and sine. All right, so the sine of 3 pi over 4 is root 2 over 2. The cosine of pi over 3 is 1/2. Cosine of 3 pi over 4 is negative root 2 over 2. So watch your double negative there. And then the sine of pi over 3 is root 3 over 2. So I end up with root 2 over 4 plus root 6 over 4, which I think was similar to an answer we got earlier. Really, yeah, is that the same one? Yep, same answer. So interesting on that one. Okay, so number 5, suppose that we have some angle that we call alpha. We know its sine. We don't know the measure of alpha. We do know alpha is in the second quadrant. We also know that there's another angle called beta. Its sine is 1/2. This one is in quadrant 1, and so we want to find some items. So I'll pause the video. Go ahead and give this one a try on your own. Okay, to do this problem, I start off with making a picture. I drew an alpha angle in quadrant 2 and a beta angle in quadrant 1. I dropped for both of them a right angle in there, since if we use right triangles, we can interpret this better. So sine is opposite over hypotenuse. So the opposite of alpha is 4, the hypotenuse is 5. This is a triple. So cosine is 3, but if you think about the second quadrant, x values are negative. So this x coordinate here is negative 3. So that will be important. Now this is not quite in a unit circle, because notice for here, my radius is 5 for my hypotenuse. All right, for the beta, the triangle with beta in it, the sine, which is opposite over hypotenuse, again, is 1/2. So that's 1 in root 2. You might recognize this as a 30, 60, 90 triangle. And so I'm going to, oops, not root 2, pardon me, 2. This is then root 3. You could use Pythagorean to get that if you didn't recognize that angle. So then the cosine of alpha, if I do adjacent over hypotenuse, is negative 3 over 5. That matches what we should have in the second quadrant. Cosine should be negative. The cosine of beta, however, since we're in the first quadrant, should be positive. This one would be adjacent over hypotenuse, root 3 over 2. I now can find these sum and difference values, even though I don't actually know the angle measurements. Remember, I'm not using a calculator, so I don't know the angle measurements. I don't have a way to find the inverse sine or inverse cosine without a calculator, except for the beta angle. I recognize that one. But I would get the cosine of alpha times the cosine of beta, change the sum to a difference, and then so minus the sine of alpha times the sine of beta. So cosine of alpha we said was negative 3/5. Cosine of beta was root 3 over 2. The sine of alpha was given to us as 4/5. We could also use the triangle. And the sine of beta was given to us as 1/2. So I have negative 3 root 3 over 10. Now these will all be over 10, so I'll just go and write it like that. Minus 4 over 10. We could factor out the negative if we wanted to. It's not required, but this is an alternative way that that answer could be shown. Both are great. For the sine formula, I'll do the sine of alpha times the cosine of beta. We will keep this a sum pattern. as it started off, and then we'll do the cosine of alpha times the sine of beta. And again, we have all of these values. So we've already found them or we're given them. So the sine of alpha is 4/5. Cosine of beta is √3/2. Cosine of alpha is -3/5. And then the sine of beta is 1/2. So we end up with 4√3/10. And then also over 10 is this -3. So I'll write that with the common denominator. Number 6. This graph shows y is equal to the cosine of x plus 3π/2. And this is in a window of 0 to 2 pi. And this says it's counting up by π/2, but I think I actually counted up by π/3 in my graph, so forgive me. We want to describe the graph using a different equation, and then we want to verify that the two equations are equivalent. So I'm going to go ahead and rewrite this in a different way by using a sum formula. So I will write this as the cosine of x times the cosine of 3π/2. Change the sum to a difference, and then the sine of x times the sine of 3π/2. So then let's see, the cosine of x, I don't know because I don't know what x is, but I do know what the cosine of 3π/2 is. At 3π/2, we have the ordered pair 0, -1, and so cosine is 0. Minus the sine of x times the sine of 3π/2. Well, the sine of 3π/2 is -1. So we have 0 plus the sine of x, which is the sine of x. Now, can we verify that? Yeah, if I look at this graph, this is the graph of the sine of x. So this worked out. The graph and the trig identity all showed the same resulting answer, sine of x. All right, number 7, go ahead and pause the video. Try this one on your own. You're going to use the sum formula for sine. If you finish that one, then try number 8 and number 9 as needed. Go ahead and watch the videos or just kind of click through and verify your answers. All right, the work and the answer for number 7 is up on the screen. It looks very familiar because we keep kind of using similar angles. And so we keep coming back to a lot of the same values, just sometimes with some different signs in here. I think I have a wrong common denominator. Let's fix that. 2 times 2 is 4. All right, number 8. So the tangent formulas, I think, are just a little bit harder to memorize. You might want to put a little bit more time in them. My suggestion is each day, memorize all of your formulas so that you are not trying to memorize them all at the end. Maybe make some flashcards. So for the sum formula, on the top, we're going to be adding together tangent of alpha plus tangent beta. On the bottom, it'd be 1 minus. So the sum becomes a difference on the denominator, and then we're going to multiply the tangent of each of those angles individually. So this would become the tangent of 5π/4 plus the tangent of theta over 1, and then the addition becomes a subtraction. 1 times the tangent of 5π/4 times the tangent of theta. But we don't know what theta is, but we can still simplify this because we can find the tangent of 5π/4. So 5π/4 is in the third quadrant. The cosine and the sine are the same values of -√2/2 over -√2/2 each time. So the tangent, if I divide the sine and the cosine, would end up being 1. So I'm going to rewrite this now and replace this. This would be 1 plus the tangent of theta. And on the bottom, this would be 1 minus 1 times the tangent of theta, which I don't need to write that multiplier. There is no simplification here. Resist the temptation to try to reduce this. We cannot reduce over addition and subtraction. So we would need to leave it like that. All right, so number 9, kind of similar problem. Go ahead and pause the video and give it. So similar to our last one, we will start by using the formula for the difference formula for tangent. On the numerator, the sign that subtraction stays subtraction. On the denominator, it toggles to addition. And also, like the last problem, we have one angle that we can evaluate the tangent. because we know the angle. And then we have the other that we don't know what beta is, so we cannot evaluate that. So that will remain. And then when we go through, since the tangent of pi is 0, when we do sine over cosine, it simplifies pretty nicely to negative tangent of beta. And that is the end of our notes for today. This was 5.2, day 1.